All right. So where are we starting? Well, I assume that by now that you understand the measures of central tendency, the mean, median, and mode, and the most common measures of variability, the sums of squares, variance, and standard deviation. If you're still a little wobbly on those things, hey, there's a video for that. You should go watch my video on those things. But understanding those things, we will now move on to Z-scores and understanding what the Z-score is. So here's the example that I believe we were using for variability. And you see there just a quick review, quick recap. Here are the errors about the mean, right? So x sub I minus the mean x bar. So this first one would be 2 minus 5, which gives us -3. So that's the deviation about the mean or error for x sub 1 here. And if we square those deviations about the mean so that they don't always add up to 0, because you can see here that these deviations about the mean always add up to 0. That's why we like the mean, because it has 0 net error. But if we square those, add them up, that is the sums of squares right there. Take the average squared deviation about the mean. So we just take the sums of squares and divide it by n, or really n minus 1, because this is sample data. So we're dividing by n minus 1. That would be 5 minus 1, or 4 in this case. That gives us our 9.5, which is the variance. The variance is just the average squared deviation around the mean. Take the square root of that, and you get the standard deviation. Okay, so now to the concept of z-scores, also called standardized scores. Sets of them are called z-distributions, standardized distributions, and sometimes they're called normalized distributions, but be careful because that last one is misleading, normalized. The z-transform does not make the distribution normal. If your data were not normally distributed to begin with, they're still not normally distributed after the z-transform is applied to all of them. So the z-transform does not force data to be normal. In fact, that's one of the characteristics of the z-distribution or z-transform, is that it does not change the shape of the distribution. So however your data were shaped before, however they were distributed before, they're still distributed that same way afterwards. All right. So anyway, we're going to use the same data we used to get a grip on variability. So this slide is just the second to last slide from the previous video on variability. Remember what we had done, measured the time in minutes that it took a sample of statistics students to solve a stats problem. We then found the mean time, deviations about the mean, also called the errors, right here. Figured out that we needed to square them because the sum of deviations about the mean is always boring old 0, right? If you add these up, it's always going to be 0. Added them up to get the sum of squares, took the mean sum of squares, or took the mean squares to get the variance with that tiny little adjustment to n right there. We have to divide by n minus 1. And then took the square root of variance to get the standard deviation right here. So square root of the variance gives us the standard deviation. Now, let's clear up the board a little bit and think about comparing one score to another in this distribution. Let's take this first observation right here. This student took 2 minutes to solve the problem. Was that really fast compared to everybody else? What about the student who took 10 minutes to solve the problem? Is that super long? Should we be worried about this student? Is this student like struggling? What's going on here? Well, one way to think about such a problem is to ask what is normal and what is a normal amount of spread or dispersion around normal. So normal, of course, could be taken to be the mean or the central tendency, or in other words, where in the distribution most of the observations are. The measure we're using here is the arithmetic mean, and we already have a way of measuring dispersion too, to figure out how much spread is normal around the mean. And for those who are eavesdropping in who are already stats experts, yes, that use of the word normal over and over is foreshadowing. But foreshadowing of the next video, where we'll make the connection with, well, you'll see. Anyway, we can just figure out where everybody is in the distribution relative to the mean. And in fact, we've already done that. It's the errors, aka the deviations about the mean, right? All these deviations about the mean tell us where each of the observations are relative to the mean. This is just the distance of each observation to the mean, or from the mean. That really fast, students, was 3 minutes below the mean. How do I know? Well, because of the negative, right? Since I subtracted the mean from this person's time, the negative number tells me that the mean was bigger. Or in other words, people took longer on average. But so what? Is it normal to be 3 minutes faster than the mean? We need to adjust that number 3 by the variability. We can do that by dividing by the standard deviation, which is our measure of variability. All right, so here's the scary equation. Notice that what's on top is just our old friend, the deviation about the mean, right here, right? Same as this right here. Below is the standard deviation, just that guy right there. The fact that we're using the symbols x bar and s tells us that this is the equation for the sample statistic, not the population parameter. If it were the population z-score, this symbol right here would be the Greek letter mu, and this symbol right here would be the Greek letter sigma. Anyway, notice another thing. Because everything in this equation is in the same units, remember in our example we measured minutes to complete a statistics problem, the units cancel. So in other words, this thing is in minutes, and this thing is in minutes, and this thing is in minutes. So the minutes cancel. And we are left with a number that is in units of whatever this is. So units of standard deviations, the thing that's left on the bottom. So let's do the first one to see how it works. So we're going to do the z-score for this observation right here. So what would go here on top? Well, that number right there. Yep. And what will go on the bottom? The standard deviation right there. So there we have it filled in. So there you have the number that goes on the top. There's the number that goes on the bottom. And so this is just going to be -3 divided by 3.08, about. And so that first z-score, z sub 1, comes out to -0.9733. So stop the video. I suggest that you stop the video and try the rest to be sure you understand where these numbers are coming from. All right. Did you do that? Did you stop the video? Well, whether you did or not, we're going forward. There they are. There's the rest of them. Now, come on. You could have done these two in your head, right? All right. So here they are, the z-scores, also called standardized scores, sometimes called normalized scores, but that's misleading because the shape of the standardized distribution is exactly the same as the shape of the original data distribution. The z-transform does not change the shape of the distribution at all. All right. There are a few things to know about z-distributions, and these things come in really handy later on, like in understanding correlations, the z-test, lots of other things further. Well, I don't know about lots of other things. Those are actually the only two I can think of off the top of my head, z-tests and correlations. You're going to need to understand these things. So first of all, z-distributions all have the same mean. No matter what your original data was, no matter what you started out with, once you do the z-transform to each observation in your data distribution and get out the z-distribution, they all have exactly the same mean. And they also all have exactly the same standard deviation. Because they're all based on deviations about the mean, and the net deviations about the mean are always 0, z-score distributions will always have a mean of 0. And because every number in the distribution was divided by the standard deviation of the original data, the standard deviation of all z-score distributions is exactly 1.0. Now, small differences when you're calculating by hand, that's just going to be rounding error. When computers calculate this stuff for you, they'll be exact to many decimal places. And finally, although our units cancel, z-scores do still have a unit. A z-score is in units of standard deviation. What does that mean? Well, look at that first one there. Let's see, do I highlight it? I don't think I do. I'll just highlight it with my laser pointer here. So let's look at this. Oh, this one. The very first Z-score right here. What is that? Negative 0.9733. Negative 0.9733 what? Well, negative 0.9733 standard deviations from the mean. Or in other words, 0.9733 standard deviations below the mean. How do I know below? Because remember that this distribution is going to have a mean of 0, and so the negative number tells me that it must be below the mean. A positive number tells me that it must be above the mean. All right. So the observation 0.9733 standard deviations below the mean. Look at that last z-score, 1.6222 standard deviations above the mean. In other words, this 10 right here, the original datum that we calculated this z-score for, 10 is 1.6222 standard deviations above the mean. Now, that becomes a super handy feature when you need to interpret a z-score. All right, and now we can revisit the questions that started us out. Do we need to worry about that slowest student who took 10 minutes to solve the problem? And what about the fastest student who took 2 minutes? A super stats genius or something? Well, in both cases, not really. We'll get more into it in the next video where we make the connection between the z-score and the normal distribution. But in general, an observation that's within about 2 standard deviations of the mean, meaning it has a z-score that's between -2 and +2, is not so unusual. And sometimes we even want to make 3 or more standard deviations the cutoff for what we will consider significant, unusual, or abnormal. Okay, so a little summary. The z-transform helps us to compare observations within a distribution to each other. The z-transform does not change the shape of the distribution, but z-distributions, also called standardized distributions, always have a mean of exactly 0.0, and z-distributions always have a standard deviation of exactly 1. Sometimes you'll hear z-scores and z-distributions referred to as unit-free because the units of the measurement scale cancel in the calculation of the z-score. Z-distributions are all actually in units of standard deviation. And that becomes super handy because it not only allows us to compare individual observations to the distribution they come in, so their own distribution, but it allows us to compare across distributions that were measured on different scales because we can transform them to a common scale, a scale of standard deviations. Anyway, keep that in mind when we get to correlation. I think that's the end of this video.